Have you ever really thought about how the inside of a massive dairy or a juice plant gets clean? I mean, every single day, tons of food flow through miles and miles of pipes and these giant sealed tanks. But what happens when the production stops? Let's pull back the curtain on the incredible hidden science that makes sure the food on your table is safe. Okay, so this is what we are up against. It's a phenomenon called food soiling, and it's basically what's left coating the inside of all that equipment. And look, we're not talking about a little bit of leftover cream. This is a massive, baked-on, industrial-scale challenge that happens every single day. And right away, that brings up the big question, the central mystery, really. How on earth do you clean it? You can't just send someone in there with a bucket and a sponge. These are totally sealed, super complex systems. So how do you scrub something you can't even see, let alone reach? To figure that out, we first have to really understand our opponent. We need to get up close and personal with this invisible mess itself. So here's the crucial thing to understand. Food soiling isn't just leftover food. It's way more complicated. It's a matrix of organic stuff, like proteins and fats, mixed with inorganic materials like minerals. And they all bond together, sticking to the surfaces and creating this stubborn layer that, if you don't get rid of it completely, can become a breeding ground for bacteria.
And this is where it gets really interesting. Check out how much temperature changes the game. At lower temperatures, you get this soft, kind of spongy protein fouling. That's what you're seeing on the left. But when you crank up the heat, it completely transforms into that hard, brittle mineral fouling on the right. We're talking two totally different problems that need two totally different solutions.
Yeah, this diagram just lays out the challenge perfectly. On a hot surface, you've got proteins changing shape, minerals dropping out of solution, and fats all linking together. It's not just a layer of gunk, it's practically a chemically bonded shield, and it is incredibly tough to get off. Okay, so you have a sealed machine with a baked-on, ridiculously complex mess inside. The solution, thankfully, is just as elegant as the problem is stubborn. It's called cleaning in place, or CIP for short. This is the engineering magic that lets these enormous food plants get perfectly clean without anyone ever having to take a single pipe apart. They essentially create a closed loop, circulating all the cleaning liquids right through the same lines the food went through. But how does it actually work? I mean, it's got to be more than just flushing with soap and water, right? Oh yeah, success comes down to perfectly balancing four fundamental forces. And this right here, this is the playbook. It's called the Sinner Circle, and it was actually developed way back in 1959. It shows the four interconnected factors: mechanical force, chemicals, temperature, and time. It's all a balancing act. If you have to reduce one, you've got to increase one of the others to get the same clean. So let's break them down. First up, mechanical force. This is just pure physics. You pump the cleaning liquid at a really high speed. The rule of thumb is at least 1.5 meters per second, and you create something called turbulent flow. This creates shear forces that physically rip the soil right off the surface. You can basically think of it as pressure washing the inside of the pipes. Next, we've got chemical force. This is all about using the right tool for the job. You hit the mess with alkaline detergents first. That's things like sodium hydroxide. And they're amazing at dissolving the organic stuff like proteins and fats. Then you follow up with acid detergents like nitric acid to dissolve all the tough inorganic mineral gunk. Now get this, because this is one of those fantastic paradoxes of cleaning science. You'd think more detergent is always better, right? Well, nope. For dairy proteins, as you can see right here, the fastest cleaning action actually happens at a pretty low concentration, around 0.5%. If you add too much, it can cause the proteins to clump up even more, making the mess even harder to remove. Wild, right? The third force is thermal, or, heat. Pumping up the temperature makes molecules zip around faster, and that supercharges the chemical reactions, making the detergents work better. But it's a super delicate balance. The general rule is to clean at the same temperature you processed at. Go any hotter, and you risk baking that soil on even harder. And finally, we have time. Think of this one as the great equalizer in the Sinner Circle. If you have to use a lower temperature or maybe a weaker chemical, or you just can't get the ideal flow rate, you can still get the job done. It's just going to take you a bit longer. So we have our four forces. Now let's see how they're actually deployed in this precise step-by-step sequence, a real battle plan to win the war on dirt. This flowchart here shows the whole operation from start to finish. And it's not random, it's a carefully choreographed dance where each step perfectly sets the stage for the next one, all designed to systematically break down and flush away every last trace of that stubborn food soiling. So, it all starts with a warm pre-rinse. That just gets rid of the easy stuff. Then comes the main attack, the alkali circulation to dissolve all those proteins and fats. An intermediate rinse clears all that gunk out, making way for the acid circulation, which tackles the tough mineral scale. One final rinse with clean water, and the entire system is totally purged of all soil and chemicals. The process is finished. The battle is over. But in the world of food safety, you can't just assume it worked. You have to prove it. So how do you know it's truly clean?
And this is the payoff. On the left, you've got a component that's just caked in soil after a production run. And on the right, that is the exact same part after a successful CIP cycle. The transformation is just absolute. It's not just shiny, it is spotlessly microbiologically clean. Of course, that visual confirmation is always backed up by hard science. They'll open up critical points in the system just to look for any residue. They'll swab surfaces and test them for any lingering bacteria. And for a super quick check, they use something called ATP testing. It actually uses the same enzyme that makes fireflies glow to detect any trace of living organisms. How cool is that? And this science is always getting better. New sensor technology can now monitor the cleaning process in real time. So instead of just running a fixed, overly long cycle to be safe, the system knows the exact moment the surface is clean. And look at the difference that makes. It can slash cleaning time, in this case, from over 105 minutes down to just 50. That saves a massive amount of time, energy, and water. So the next time you pour a glass of milk or open a carton of juice, you'll know about the incredible, invisible science that went into making it safe. It kind of makes you wonder, doesn't it? What other hidden systems like this are out there, quietly working behind the scenes to make our modern world possible?